ఇన్ని రోజులు వస్తున్నాయి 100 కోపంలో 130 కోపం ఇప్పుడు రావట్లేదు వచ్చింటే పెట్టుకునే
Hello everyone. Today I will be presenting Binary Lens Identity Architecture, a system designed to modernize attendance using edge deployed facial recognition with anti spoofing. The key idea is to create a frictionless, contactless, and secure system that can distinguish between real users and spoof attempts in real time. Operational drug of legacy attendance. This slide highlights the problems with traditional systems. Manual roll call wastes up to 1 hour daily. RFID cards create bottlenecks and can be easily swapped. Touch biometrics are slow and unhygienic. In contrast, our smart camera system provides high throughput, 11 plus frames per second, zero proxy risk, full contactless experience, edge deployment, meaning it runs locally without heavy infrastructure. Slide 3. The binary gatekeeper sorting the frame. This is the core concept. The system acts as the binary gatekeeper. It divides all the inputs into two classes. Class 1 authorized users, which are known, verified, and logged. Class 2 unauthorized or spoofed inputs, blocked and alerted. So every frame captured is instantly classified into these two categories. Now comes the main part, that is the pipeline. Stage 1 being detection and isolation. In the first stage, we detect faces from the input frame. The images is converted to grayscale to reduce computation. Then HOG features are extracted to identify the patterns. A Haar cascade classifier detects facial structures like eyes and nose. Finally, we generate a bounding box, isolating only the face and removing the background noise. This ensures the system focuses only on relevant data. Pipeline stage 2 spatial alignment. In real world conditions, faces are not perfectly aligned. They may be tilted or off center. So, in this stage, we detect facial landmarks like eyes, nose, and jawline. Using models like ResNet 50, we identify key anchor points. Then the face is rotated, scaled, transformed into a standardized format. This ensures consistency before feature extraction. Stage 3 Feature extraction using the 128 dimension embedding. In this stage, the system converts the face into a numerical representation. Instead of treating it as an image, a convolution neural network extracts geometry and microfeatures. This results in a 128 dimensional embedding vector which uniquely represents a face. Even with lighting changes or slight aging, this vector remains stable, acting like a digital fingerprint. Stage 4 Classification and Decision Boundary. Finally, we classify the face. We calculate cosine similarity between the input vector and stored database vectors. If it lies within a known cluster, which is class 1 authorized, if it falls outside, then it is class 2, which is unknown or spoof. This decision boundary ensures accurate and fast identification. Now comes the next slide. The anti-spoofing shield defeating presentation attacks. This slide explains how our system prevents spoofing attacks, also called presentation attacks. On the left side, we have a spoof attempt where someone tries to fool the system using a photo or printed image. These attacks fail because the system detects texture, flattening, and zero depth, meaning it recognizes that the input is not a real 3D face. On the right side, we have live verification of an authorized user. Here, the system checks for micro movements and depths, confirming that the face is real. We use a lightweight model like MobileNet V3 to analyze features, textures, pose, and light reflection. Additionally, we implement passive liveness detection, which works automatically, and active liveness like blinking or smiling checks. Together, this creates a strong anti spoofing shield. Zero Trust Biometrics Encrypted Storage. This slide focuses on securing biometric data. The main vulnerability is that storing facial images or plain text vectors in databases can lead to identity theft. To solve this, we convert face data into a 128 dimensional embedding vector, which is numerical representation instead of an image. Then we apply hybrid encryption using AES 256 and FERNet, ensuring data is secure both at rest and during transmission. We also add dynamic defenses such as initialization vector randomization, role based access control. The result is military grade security, reducing privacy risks significantly while maintaining real time performance. The engineering trade off accuracy versus real time latency. This slide shows the trade off between accuracy and speed. We evaluated multiple models like DLib, Ghost FaceNet, ArcFace, SFace. On the graph, y-axis is accuracy and x-axis is latency. We observe that deep models like ArcFace have high accuracy but high latency, and lightweight models like Ghost FaceNet are fast but less accurate. In real-world scenarios like classrooms, we need both speed and accuracy, so choosing the right balance is critical. Model selection matrix identifying the Goldilocks zone. This slide summarizes our final model comparison. We evaluate models based on top 1 accuracy, AUC score, throughput in FPS. From the table, arc pace is accurate but too slow, S pace is balanced but not reliable enough, Ghost FaceNet lacks discriminative power. The best choice is DLib, which achieves highest accuracy, best area under curve, and fastest throughput. So it lies in the Goldilocks zone, not too slow, not too inaccurate, but just right for real time applications. Thank you.